Xavier will give a talk on alternative tableau permutations and partially asymmetric exclusion process.
Thank you. Thank you very much for the invitation. I thank the both organizers for this invitation in this prestigious institute, this prestigious colloque. The talk, as I say, is in everything is in true transparencies. Usually I use transparencies. Now I use the computer, but I go back to my own to my favorite. So the talk, you see, some first, second, 3, 4, 5, 6, 7, 8, 9, 10. The talk is in 10 parts, 6 minutes for each part. If German is good, 60 minutes. Okay. Good. So I'm going to talk about some combinatorial objects, the very classical permutation, and a very well-known physics model called PASEP or ASEP, or partially asymmetric exclusion process. This afternoon there will be 2 talks, one by Kiran Malik, the physics point of view, and so this is very old, very classical in physics, but in combinatorics this is not such classical, and since 2 or 3 years, a lot of combinatorists have discovered that there is very deep and nice combinatory behind this. So I would like to add one more stone in the story about this, to take an alternative approach to everything that we've done before by combinatorists. I define alternating tableaux, so it's a new definition in this very classical field of permutation, at least to my knowledge. I never see this before. So I take a Ferrer diagram, or if you, in physics, a Young diagram, but you allow, you see, some column or some row to be empty. So you have, from this point, you go down here, you get a path of length n, and if you go like this, you get a path of length n. So n is a total number of rows plus a total number of columns, and maybe some row and column are empty. N is fixed. So definition. I am going to take a certain coloring of the cell in 2 colors, red, blue. When I mean coloring, it may be empty coloring. So some cells are empty, some of them are colored. Maybe you cannot color everything because I'm going to put some restriction on the coloring. It's very easy to count how many such things there are. Wait, Newton is coming soon, so please. No divided difference. Okay, so the condition is for every blue cell, you don't have any color cell on the left. For any red cell, you do not have any color cell below. As this is the main definition of all the talk. The key definition, I repeat it a second time. With another picture. So an alternative tableau is a filling of this, you say, with blue and red. And the condition can be visualized this way. See, this brown line means there is nobody colors on the brown lines. Some brown lines are horizontal, some are vertical, and some may be cross. So this is the main definition. Now the main theorem, and you can, the whole talk is about this main theorem. Proposition, the number of alternating tableau of size n. N, you remember, is the length of all this. Here, n equals 12. The number of such tableau is n plus 1 factorial. Easy. You say, come, exercise. Let's n equal 2. That's true. 3, 4, 5, okay. So, section 6 minutes, okay. Section 2. I have not to forget to remind me each time I introduce a new section. Voilà. So that
Only afterwards or before the section?
after. Because just to remember you, if you sleep or if you forget, because sometimes I go very fast, so don't listen, just look too transparent. The alternative bijection. It's going to be an algorithm, a bijection between alternative tableau and permutation. I define the following classical notion in combinatorics. Let's take a permutation, like this one. Here is this permutation on 9 elements. And I will say that the value x is, I think in English it's advance, and recul is recoil. When you go forward or backward. Christian, help me, what is the name?
Forward,
But avance, recul. Hein? I keep it in French. Avance, recul. So x is an avance or an recul if and only if you take the next value x plus 1 equals sigma of j, and j is bigger or less than I. For example, say I've put in blue 7, 4, 8, 5, all the advance. 7 go to 8. 4, the next one is 5, the next one is 6. Now the next of 6 is 7. So in red are the recul, when x plus 1 is at the left of x. And by convention, 9 is the recul, is going to infinity. Minus infinity. Mais c'est petit. There was many cyclic things in this. So now I write this in this way. Here is my permutation. In blue, all the value of advances. In red, all the recul, except 6. 6 is a recul. It's good. But I put it in green. Yes, this is the rule. You have to accept it. That's the last letter. The last letter, you put a line in green. Okay? Now all the blue, there is 4 blue balls. You put them here. You put all the red on the left, all the red on the right, and the last one in green. It's important, but in the construction it's useless. But you have to put it. And now you imagine that the number, they are going down. They are ball falling down. So 2 and 8, they fall down and they cross. The rule is each ball is following, a blue ball is following the blue thread, and the red ball are following the line in red. So easy, huh?
Keeping the order.
We'll see.
Be patient. If I keep the order, I will not get any bijection. You have to do something more subtle. So, okay, it's wait. I am in the computer science department, and we think in an algorithmic way. So the best way to learn an algorithm is to make it work. And slowly, the rule is going to appear, and at the end, you will be convinced that something deep is coming with a bijection. So, the next is 3 and 4. They will not allow it to cross because they are consecutive. X plus 1. So, the greatest of the two is going to survive and kill the youngest. The 3 disappeared and make a 4. And the 4 follow his route. If I go back, you see, when each time you have 2 consecutive points, maybe the biggest is on the left, maybe the biggest is on the right. So you put a blue or a red point according to this condition. Here 4, the bigger the 2 is on the left. I put a blue point, 4 go down, and 3 disappeared. So 7, the road is free. There is nobody who is going to disturb it above. 1 and 5, okay, they can cross. And 5 fall down on the ground level. 8 and 9. We are now, again, with 2 consecutive balls. Now the maximum is on the right, so you understand, I put a red. The 9 is going to go down, and the blue disappeared. 4 and 2. Now a new rule is going to appear. 4 and 2, in fact, they are consecutive in the restricted for the value you see. There is nobody between the 2. 2 and 4. The 3 has disappeared. So I consider them to be consecutive. So it's a blue point. And the 4 and 9, the 1, now 1 and 4. The 2 and the 3 have disappeared. So a blue or red ball will be created. 4, 7 and 9. The 8 disappeared also. So a red point disappeared. So some values survive. The green one is the master of every day. Nobody has disturbed it. Now you take off all this. And what you see is the coding of the bijection in terms of an alternating tableau. Because the blue line are the column of the tableau. The red line are the row of the tableau. Take the first column. This cell corresponds to this. Second column, see blue, blue, nothing, blue. Blue, blue, nothing, blue. So it's another way, this picture, to write it as an alternative tableau. So this I call the exchange deletion algorithm. And it's a bijection. If I have time, I will give you the reverse bijection. But believe me, it's a bijection.
State me in which order you process the things.
Any order. The result will be always the same. It's a non-deterministic algorithm. At the end, I always get the same alternative tableau. Yes, Philippe?
What's the order of the green line?
Very important. To understand the whole, you have to do the reverse bijection. And this is why you have n points. In fact, the bijection is with n plus 1. The number of alternative tableau, it's n plus 1. The n plus 1 comes from the green line if the length of the path is n. So a more classical notion, if you take the inverse of the permutation sigma, take sigma, take the inverse, then the indices, when you have a permutation, there is the indices here, and here I call this the value. So the indices, the sequence of indices of advance of recul, this word in 2 letters we have in blue and red, become what is called, it's related to the Hebdon sequence of the permutation. It's not the Hebdon sequence of the permutation. It's let's take, for example, 8. 8 is an advance. It goes to 9. So it's index 4, so in advance on 8. Now 4 become a value. This is the index is 8. And you see 4 is a rise. What we call is a rise or a descent. A rise or a descent, it's a value such as the next value is going up or going down. So this is called the up-down sequence of shape of the permutation. And what I have here is, in fact, some people call this the Genoki shape of the permutation. It's the word you get on looking each value, 1, 2, 3, 4. If it's the next one at the right is just going up or going down. So in other words, you see, you can put this way by taking the inverse. that you have a word 1, 2, 3, 4, 5, 6, 7, 8. You have a word in 2 letters, and I can say that the number of permutation on n plus 1 element having a given shape, a given Genoki shape, which means that, for example, 2 is a rise, 1 is a rise, 3 is a descent, 4 is a rise. It's the value. See, 2, 1, 4, 2, 7. You get them 1, 2, 4, 7. They are the value for the rises. So in blue is the rises, in red is the value of the descent. So in other words, there is a bijection between alternative tableau and permutation such that the shape, the Young diagram, the Fair diagram below, it's a coding of what is called the Genoki shape. And you can say, why Genoki? It's some people in there's a recent paper on Genoki shape and etc. It's because in the case of an alternating shape, everybody knows that alternating permutation, it's up-down sequence alternating, just give you tangent sequence number. But if I take an alternating shape, then I get the Genoki numbers. And the number of alternative tableaux having this alternating shape is exactly the Genoki number, which is close to the Bernoulli numbers. Genoki, and Genoki is related to tangent numbers, the number of alternating permutation on 2n plus 1 letters. This comes from, there's a lot of combinatorics. This go back to Dumont permutation 20 years ago. So I'm talking about Genoki, 19th century. So I love history of mathematics, so let's make a drop of history. And we are in a historical place. So.
Oh, this is not a new chapter.
No, it's not a new chapter.
6 minutes have passed for this.
But some of them are long, some of a drop of history. You know, at the time of this is Jacob Bernoulli number. It's brother. Jean, maybe you should. I don't know. The light is maybe. Do you see the picture? Yeah. And the same time was, of course, it's Isaac Newton. And look, here is the Bernoulli number in the fracture alphabet in Gothic, and here the 2 power 2n, the tangent, the second. This is in Latin. And who have written this? And here is the Genoki number 1, 3, 17, and who have written this? It's at the same time as Leonard Euler, 100 years before. Euler is related to St. Petersburg Academy, Pierre Le Grand, and Berlin. And again, my good master was here is Genoki numbers again. So this is a great master in a certain way, talking each other among centuries. You jump from Euler to André, and then to Schutzenberger and go back. Okay, the end of 6 minutes, the passep. Now. Okay, so. So the passep is this is a general passep. So, everybody understand? No question? I go further? Okay, so maybe Kieran will talk more and give the definition. The passep, you have a finite strip. Some exclusion process means there is at most one particle in the cell. It's empty or filled by one particle. And then there is a Markov process, a process which at any time, you can do this in continuous time or in discrete time, but let's say that if the cell is empty, then the particle jump. And then there is a reservoir, infinite reservoir particle here, infinite, and then also here. And if it is empty, it's getting with probability alpha dt. In the infinitesimal term dt, it can enter with probability alpha, it can go out with probability beta. And the general model, you can even go, if you have decided that this is not good, you go away, and here you get in by not the regular way. You can go in and back, get in or get out or in both sides, and Q, you go back if it's empty with probability Q dt. Or you can say this in discrete time. You choose by random one of the wall. There is n plus 1 wall, and if If a transition is possible, you do it with probability 1, Q, alpha, beta, gamma, delta. So this is really a toy model. It's very good and nice and beautiful, and because this model is simple. After certain relaxation, there is some stationary state which appear. There's a unique stationary state. This is a paper I will refer many times in the talk of Derrida, Evans, Akib, and Basquiat. And so for any word in 2 letters, there is a system of stationary probability. And this model is modelized many situations in the real life. It's simple enough, but it's complicated enough to have a very nice phase transition. And it's a good model because I think in Geneva they take this model. I read there is this model to modelize to make in real life the traffic flow in Geneva. They use the PASEP, the TASEP, because PASEP you will on the highway. Q is very small if you have completely drawing, but it's possible. Some people go. So I will write there is a function for any word in 2 letters. There is a function f divided by the sum of all the probability to make a probability. This is a partition function, and this is a fundamental matrix on that. And suppose, so this is a paper, a fundamental paper, seminal paper, that suppose there exist D and E matrices, in general infinite matrices, satisfying this commutation relation. Suppose there exists a column vector and a row vector such as that you get this border condition, then the stationary probability is given by this formula. What does it mean? It means that if you have a state, any state is a word in 2 letters. Empty, occupy, etc., etc. So it's a word in D and E. So if you put D equal, I think D means occupy and E means free cell. So this is a word in D and E. You apply both sides, W and V, and you get the function Fn, divide by the partition function, and you get the probability. So in this talk, the general model is very complicated. There is some remark, Chairman? Not Chairman, but the first boss. So what have we done in combinatorics? They give a lot of papers, give some combinatorial interpretation of this probability in terms of many different things. In the case of gamma equals 0, this is 0 and 0. We don't know to do purely combinatorially the general model, to my knowledge. And if you put Q equals 0, that happens in Geneva in a highway usually, it's a TASEP. Every particle moves in the same way. So in the first talk you have seen NR, he talked about Bertrand about the TASEP. There was many TASEP in this talk. So this paper go back before the matrix on that. In fact, there was a nice paper by Zalberger and Shapiro. They were connected with some biology, which gives straight away the probability stationary. In the case Q equals 0, alpha equals beta equals 1. The most simple case, which says that the probability is exactly, so such a word in 2 letters you transform it into a path, particle is north, east, etc. And the probability is the number of paths which are below the green path divided by total number of pair of paths like this is Catalan number. And then later, so there was some other computational interpretation with TASEP to explain. So many people in Melbourne, in Paris, in Bordeaux, in Toronto, and then the PASEP with a Q. So there was many different computational interpretation. Sometimes with path, sometimes with permutation, with binary tree. So when you are in the TASEP, it's a combinatorics of Catalan number. When you are on the PASEP, it's a combinatorics of n factorial of permutation. So now I give, after all this interpretation, I give a new one with alternative tableau. So what they have done, usually the commentarist, I don't know why, the matrix on that, for me, it's nice. So they try to prove everything without using the matrix on that, or with direct proof, for example, by taking a Markov chain, a bijection on permutation, which project the Markov chain on the state. But for me, that's a starting point. Maybe, if you know, a matrix on that, what I understand is equivalent more or less to beta algebraic on that and everything. So this is my starting point. I claim that if you take any word in E and D, then when you apply this commutation, suppose you have a word, you say you have a word, then I can take any way here and then replace. You can make the computation, and then DE can be this or this or this. So if you start with a word, you are going to get a big polynomial by putting all the E on one side, all the D on the other side, by using the commutation relation. So I claim that what you get at the end, anyway you do the rewriting in the algebra, in the quadratic algebra defined by this equation, I claim that this word is equal by rewriting to the sum over all alternating tableaux with the profile. The profile is a border, the contour. Q is the contour of W. So Q is power the number of cross. It will come in the next part. E, Q comes from this. E is the number of columns without a red cell, and J is the number of rows without a blue cell. And I give you a proof, and you will understand in the proof what means number of this. So what I'm going to do is, instead of rewriting in a stupid way like a word, and I am going to make the rewriting rule in a planar way. So you see DE, D multiplied by E can be E multiplied by D. And I will put a Q. This is a cross. Or maybe DE can be equal to E. But I will do in a planar way, means DE equal E multiplied by the identity. I am going to color all the edges of my diagram in blue or red and in brown. Thank you. This is identity. So I need some more rewriting rule. Of course, DI give ID. EI give EI. I by I give I by I. Let's do it.
It's not that different from the original algorithm. Relative.
It's not different of the original what?
It's different.
From
the
what?
original algorithm for the bijection, the injection. Well, it has some ideas in common.
Well, everything is, there's a flavor of, we will see. So let's do DE equal ED. I have made the substitution with a Q. Here I have made DE equal E. Here, this was the identity, so okay. So here I made a Q, you see. Here I make a blue. And you see, when there is the identity, the brown line, then it's going to propagate. And you immediately feel that on the left of the blue cell, there will be nobody. Allez, hop. So you see, the propagation of the identity may give you the definition of the alternating tableau. Hop, chop, no. And then this word is equal, after all this rewriting, is one of the terms of the big polynomial is e to the cube multiplied by d. And you see the d, there is no red in this column, and the e, there is 3 termini, there is no blue in the row. And that's the proof. Consequence, if you apply now the matrix on that, and exactly you put all the e on one side, all the d, and because of its border relation, this is going to be disappeared, all the e and the d is going to disappear as soon as you suppose that this is 1. And then I get my theorem as an interpretation of the stationary probability. but I don't need to know what are D and E. There is many different solutions of the matrix on that. I don't know I just need to know that there exists this such as this. So I start at which time? Good. With the modern technique, Chairman, it's on my computer, it's written exactly when I press, it's 28 minutes and 46 seconds.
Close enough.
So it's, I should be, oh, I am close.
4 minutes late.
Huh?
4 minutes late.
Yes, but you know, at the end of his talk, he's going, he's giving the second part of his talk at 5 minutes of the last 5 minutes. But I go slow. I go slowly because it's the main definition. Now, so many people are working with permutation tableau. I receive by email the logo, there is abstract. We want to have the preprint. We want to know what are these alternative tableaux. So this is a kind of video Newton archive preprint because it's on the video. It will be on the web. So and all the slides will be on the web with the references. So permutation tableau. So this was another interpretation of the PASEP. And the permutation tableau, it's the same. You have a certain Ferrer diagram in general included in a rectangle K by N by Nk, and it's called permutation tableau if and only if. So now we have only one point, one color. There is point, some cell have a point, black point, black equal, it means 1. Usually in the literature they put 1 and 0. Here I will put anti-cell, or because we're in physics, or a black point. And first condition, in each column there exists at least 1, 1. Second condition, this is forbidden. This pattern is forbidden. Maybe I write this here because if you have an empty cell, you cannot have this. This is in the French notation. This is the British or American or Anglo-Saxon notation, and this is forbidden. So this letter is, if you reverse it, it's an L, and this is le. And this sometimes it's called le diagram. It's Postnikov who introduced this le diagram. If you have only the condition 2, then Postnikov, in a very nice paper, it's a 60-page paper, he introduced this tableau. This is related to algebraic geometry, to Grassmannian. Each Grassmannian is a bijection with a Ferrer diagram, and the positive cell of the Schubert cell is exactly in bijection with the 0, 1 tableau satisfying only the condition 2. But if you make only 2, this is bigger than permutation. To get permutation, you need condition 1. And this is not very nice because you destroy the symmetry in row and column. And then, whoop, yes. So, Loren, William, and Sylvie Cortel, they show that you can interpret the probability of the PASEP with this tableau. There's a very nice paper also with Einar Steingrensson and Eric Javik, and because related to a lot of subject in permutation with forbidden pattern, everything. So there's a lot of commentaries behind this. The total number of permutation tableau is 10 factorial, and there is many bijections have been given. The original Postnikov bijection was in fact with what is called decorated permutation. But there is many bijections by Cortel-Nadeau, etc. So I am going to introduce a new one, but not between this tableau and permutation. I'm going to introduce a bijection between alternative tableau and permutation tableau. So we can, by combining the first bijection, we have another bijection. So here is an alternative tableau, and I'm going to show you the bijection with permutation tableau. So this will go fast. Don't read the instruction. It's just a movie. Just look at the picture. Don't try to understand, because the slide will be on the web, and the specialist will read carefully how to go from one tableau to the other. So don't read, just look at the picture. So alternative tableau, and there is a sequence of steps. Don't read. Tac, 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 et voilà. You have a permutation tableau. Proof it is a permutation tableau. Don't read. Bijection inverse. I take a permutation tableau, and I'm going to transform it in alternative tableau. Do this. Tac, 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 top, 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 top. Et voilà. No, it's that's you get it back. Proof. This is in French to show, because there was to show that the interpretation which is known in terms of permutation tableau, if you use this bijection, you get immediately back the previous interpretation of the people, all the people I quoted before, in terms of permutation tableau. So, next.
It also induces an evolution in the space, not an evolution. Well, you can do it right or left.
I am late on my time, so please. Aha, this is more complicated. So, permutation tableau.
In fact, you have more time.
We will see. So if people are tired, I will. Maybe you will decide after 60 minutes if you give me.
Last question.
If you give me 1 minute more or 5 minutes. I don't know. So, because you are not, you have seen all this. It's come from braid, go to algebra, you send on temporal algebra, the John polynomial, the trace, temporal algebra is Catalan number. There is some Catalan number in the note. So, there is a Catalan inside this tableau. I call it Catalan alternative tableau. So when you have a tableau, you see there is some, this cell coming from the Q. When there was a parameter Q, each time you have a cell like this, you have used the rewriting rule DE equal Q. An alternative Catalan tableau, there is no cell like this. This is forbidden, which means you never use a Q, which means Q equals 0. So if I make Q equals 0, I get a set of tableaux which are counted by the Catalan number. Back to 1836. Catalan. In fact, Euler defined Catalan in a letter to Goldbach, which was discovered after this paper by a grandson of Euler. He discovers a letter to Euler to Goldbach introducing triangulation of a regular polygon. And if you look the date of the letter and the day where he sent this paper for the famous Euler polyhedral formula, there is in this related to this some triangulation of polygon. So this is probably why Euler introduced it. So this is so I don't have yet made the transparencies with Catalan alternating tableau. This is a Catalan permutation tableau. In terms of permutation tableau of before, there is only one in each column, at most one. And this is in British notation, and I gave a bijection. There was many bijections, but there is one with binary tree, so I switched to the French. And to make everybody happy, I switched to my own notation. This is what we use in our village in the south of Bordeaux. And so there is a bijection between this, and this is the end of the section 6. That there is a nice bijection. No, so far. There is many bijections, but I love this one because this was submitted, in Tianjin, in China, the last at Pessac. You have a bijection between this and this with binary tree. And so you can say, but where is the word in 2 letters? The word, you look the binary tree and look the ending edges. You see some are on the left, some are on the right. So of course, the first and second are always, but if you look here, you have red, blue, red, so you have a word in 2 letters. And the probability, the bijection is, the word is exactly the shape of the Fourier diagram. And now if you ask, what are the probability alpha and beta? They are exacting counting the number of elements in the left and the right branch. So this bijection is useful because there is a symmetry on the binary tree, which explains the symmetry in the intercept. You can always reverse, change alpha and beta, everything. La guerre history. So now the second part of the talk. is to explain you, I have explained you from where this alternative tableau came. It's just by rewriting the rule of the matrix on that. Now I am going to explain you how I found this bijection with the ball falling down. Because when you give this straight away, you can sometimes impress people too. But I'm going to explain you how I construct it. It's a nice example of way of constructing a bijection by knowing, by going in a beautiful walk in the bijective combinatorics garden. So we are going to go in the garden of combinatorics, and at the end we will fall down on the bijection of the beginning. So I need some ingredient. I need the bijection, the Laguerre history. Laguerre because of orthogonal polynomial. So definition, a Laguerre history of length n. First, there is three things, gamma, C, F. So gamma is a Motzkin path in green. C is the coloring of the level on two color. Motzkin, you know, it's like a dict path, you put some level. F is a function in blue. It's a vector of 1, 2, 2, 1, 2, 1, 1, 2 of numbers with a condition they are between 1 and a certain weight, the valuation, each step going down. No, every step is weighted by the height of the vertex. For example, here I start with height 0, 1, 2, so I take k plus 1. The height of the vertex is 3. So you see the yellow number are the height of each vertex, and I choose any number between 1 and the height. So if you fix this, the total number of possibilities for F is a product of the height of the vertices of the path. So here is the bijection, the weight of the fourth step. And I claim that the number of such history, we call history because it's a background from computer science. Let's go back to Françon 30 years ago. Histoire, data structure, history, fichier. This means you are performing some elementary operation. And each time you perform an operation, you have a choice. And you remember at each time which choice did you do. I claim that this is in bijection with permutation. And I claim that this explains combinatorialism, that the moment of the Laguerre polynomial are n factorial. In fact, here I am with Laguerre for alpha equal 1. If I have alpha equal 0, I should have Laguerre with n factorial. We know Laguerre, any orthogonal polynomial satisfies a recurse like this. You have a bk lambda k. It's equivalent to a Jacobi quantity fraction. And all this Laguerre bijection explains this. And here is a bijection between Laguerre history and permutation. So you have your path, you have your choice, and here is a bijection. The idea is you start with the empty cell, you fill up the empty cell with 1, and depending if you are going up, down, or a level, each time you are going to create a new empty cell on the left. Maybe you don't create any new empty cell, maybe you create one on the left, maybe one on the right, and maybe both on both sides. So when you, for example, here, check 5, I don't create any empty cell. From this to this, I don't create empty cell. And 1, 2, 3, 4, 5 is because I was going down. When you go down means you don't create any, you don't do nothing on the left and right. If you go level, you put a cell on the left or a cell on the right. The number of empty cells will keep invariant. If you go up, like here, when I go from the number 3, for example, you put the 3 here. So you create a new cell both sides. Okay, so the number of empty cells is exactly the height in the dict path. The way you put your empty cells left or right is the color of the level. And now you have some choice each time. When I go here, you see, I put my 5. There is 2 possibilities. So I label the possibility from left to right, and my 1, 2, 3, my 5 was possibility 2. See, the 4 was possibility 1. So for the 4, there was 3 possibilities, and I put it in first position. Ça va? No? You feel the Laguerre ambiance, and now I am going to. So now I'm going to make an incarnation of my operator. Before, D and E was pure formal letters with the writing. I am going, as a computer scientist, to implement D and E on something. So, I consider the vector space V generated by all alternating words in 2 letters with no occurrence of white, white, black, black. Which means that the elements of length n, there are only 2 choices.
Exactly.
So maybe you feel Xavier is becoming a little crazy. Very elementary, but it's fundamental. Like the green line I put at the end, at the beginning of the talk. Now I define 4 operators. A, S, J, K in this following way. A, take a word, is the sum of all the words you get by replacing each letter white by this. S, so A for adjunct, you add a new white letters. S, you sum of all letters Y, and you replace the white by black, but you do this rewriting also. You are not allowed to put black together. So each time you do this, and you have a sequence of black, you replace it by a single black. Example, take this word, apply operator S, I put this in black, which gives me this, and I put this here, which gives me this. In other words, this equal if I have, d'accord? And then the 2 other operators, you replace each letter and you put a new black, new white. So you are feeling that these 4 operators are related to the 4 way of filling my empty cell and putting maybe I cancel or it's coming, the relation between this and Laguerre history. So believe me, this operator satisfies this commutation relation. Proof, you have to really look. Suppose I have really 2 white cells. This is some part of the world. I have 2 white cells which are really apart from one together. So I replace A, I do S. If I do S and then A, then no problem, it's commute. But if you do A and then you cancel this white cell on the left, then you cannot commute. So this is exactly the operator J. And if you cancel on the right, this is exactly the operator K. So this gives you an idea of the commutation. Same thing for A and K, and this, and this, and this, and that's the proof. You feel it. So I have this. Now I put D equal A plus J. E equal S plus K. Few computation, Jeff, give you DE equal ED plus E plus D. I get a representation of the matrix on that with the commutation of the PASEP. So here is my Laguerre history. Here is the way. In fact, if you want to remember each time, see the way of filling up and the way of the path, the elementary step in the path is exactly a sequence, corresponds to the sequence of this operator.
What about Q?
You can't put Q in that. You can put a Q in each commutation, everything. Yes, it's well, it's work with Q. Now I need another.
You just shifted.
I need another tool. Yes. Now coming from RSK, Robinson, Schoenstatt, Knuth correspondence. So I need this idea to go further. So everybody know permutations in bijection with a pair of 2 standard Young tableaux. Representation theory of symmetric group, it's a very simple case. But Schutzenberger invent the jeu de taquin. You can get the P symbol, that's the P and the Q, and you can get the P symbol, for example, for this permutation. I start, usually we put 3, 1, 5, 3, 1 like this, but it goes faster. You see, to put it like this. So the number go increasing in each row from left to right, in each column from bottom to top. So you take you get a certain skew Young tableau. You can still read the permutation. And the jeu de taquin is to try to fill the cell which is below. And there is 3 different blue cells. And the game is you choose any one of the 3. For example, choose this one. And then you are going to move the smallest of the 2 on this cell. And if there is a new hole in the tableau, then you apply recursively this hole. And then at the end, you get something here which is 1 cell less. And then you repeat. It's a double recursion, you repeat, and you get this. And anyway, any choice you do, you get the P symbol of RSK. And to get the Q symbol, you need 2 P and Q. You do the same for the inverse permutation. So this is RSK. It's a very beautiful bijection. There are hundreds of papers on this. There's many different ways to define it. And Sergei Fomin, I think, is the initiator of defining it with a local rule in the following. Oh, you can put a Q, but this was the algebra we get with PASEP and factorial. But if you take this very classical relation, Heisenberg, the creation and deletion operator in field theory, you get this relation, and you can construct RSK from having a representation of U and D. And U and D can be represented. It has been done in the first talk by Yenard. In fact, he created U in this way. Take a Ferrer diagram, the operator U, or if I take the vector space generated by all Ferrer diagrams, the basic effect diagram, U is to add a new cell in the diagram. D is to delete a cell. So if you look this like this, if you look tac, 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 and you do only operator U, all possible U, then you go back to the talk of De Geer, which is going the first, the second, the third, and you have to keep, you see, always a Ferrer shape. In fact, if you just use a U and you label the thing like this, you get the nil topology label algebra, which is isomorphic, which is the same dimension as the topology label algebra. But here it's more. I delete, I add, I delete, and you are moving on the Young lattice. And why there is this relation? Why they commute? Suppose you add a cell here and you delete this one. You feel it's going to commute, but some special case. You add and delete. Then the Young tableau, the diagram remains the same. Or maybe you delete first and you add. So doing first add and delete, you see there is this special cell. And the problem is that there is one more yellow point that there is 1, 2, 3, 4, 5 possibilities like this and 4 like this. So this interprets the I, the identity. Now the idea of Fomin, Sergei Fomin, is you start with a grid. Make you start with the empty Ferrer diagram. If you take only a sequence of U, you get a Young tableau. Now only a sequence of D, you get a second Young tableau in a reverse way. And the idea is now make the same. UD equal DU maybe identity. So here you get a Q, etc. So what you are going to do, analog to alternating tableau, but what you get, you see, it's the same thing. Same idea. Allez, hop. So the green color now. So now, in this particular case, I don't want to have any words. You can have any words in U and D. You put back here. What remains is the empty word. Because I want to compute, starting from the empty diagram, applying n times U, then n times D. I want to compute the coefficient on the empty diagram. And I know, by Robinson said, that this is a pair of Young tableau, which is n factorial. So I mean, I must have on each row and column no more blue or red edges. Everybody is identity, which means that there is one. See, it's analog of alternative tableau, because now the point, there is nobody on the left and nobody below. And if in each row and column there is a cell, this means it's a permutation. And that's the proof that the number of permutation is the number of pair of Young tableau. And now comes the main idea. The key idea is that.
So maybe what were the white scores? Are you explaining it now? What the white scores are?
Well, it's a whole talk. It's on my website. I make a pedagogical introduction to RSK. There is two. So I just go very fast. So here is Ferrer diagram. Means empty Ferrer diagram. So I put the edges. So each time you have an edge, a blue edge, for example, it means you are adding a new cell. Here you do nothing. I add a new cell, you see. When I go D like this, I am deleting, or going backward, I add. Each time you go up on the red edges, this Ferrer diagram is obtained by adding a new cell. Each time you go this way, this is obtained. So the philosophy, I have no time to explain completely this, but the philosophy is that you have applied here the rule UD equal DU. So the philosophy is that, first the local definition of RSK is that if you know, you put some empty diagram here, and then you fill up the whole square, but if you know the 3 diagram here, then you know the 4th one. So there is some rule, local rule. This is called local rule. They are complicated. I cannot tell them, I mean, here. And conversely, if you know this is a P symbol, this is a Q symbol, if you know this, so you know these 3, then you can know this one. So there is some local rule. You see, there is a precise algorithm which go in any way, then you can reconstruct the permutation from one side or another. So now the local rule, I don't tell what is there, but the philosophy is that each time, you see, here I made a commutation. And for this commutation, I have a very simple explanation by on my Ferrer diagram, the one I showed you before. There is one more way of adding. There was a simple explanation, and doing the rewriting, it's just rewriting in the algebraic words, and I am propagating across this network the simple explanation for each square. The simple explanation of the way, and but you have to make a convention of one more of the les creux, the yellow point. There is one more than two. You have to pair them 2 by 2 and make one apart. So if you put the one apart below and you pair them 2 by 2, you get the RSK by insertion in the row. If you do the reverse, you do insertion in column. But you can pair them 2 by 2 in any way. So there are infinite number of RSK. So that's the idea, the philosophy. And last, so combining all this, if you have in mind the orthogonal polynomial, the Laguerre history, if you have in mind this local, which came from commutation. Now we have some commutation. We have some commutation explanation. Go back now to the Laguerre, to the PASEP, to this operator K, J, K, etc. Go back here. Take a permutation. This is replace. You see, you cancel the 9. You cancel letter 8 and 9. You can deduce this by cancelling at each level all the letter 9, 8, etc. until you cancel everybody. And then this is a Laguerre history written as a path. So the operator says you add a new cell. Remember the Laguerre history. And this is written in terms of operator with 4 operators. So A, operator A, on the horizontal edges there is A or J. Because D equal A plus J, you have a choice there. Or on the vertical edges you have S or K. So these 4 operators correspond to the 4 possible steps in the Motzkin path, and which correspond to exactly the Laguerre history. And now I do the same as doing with for Robinson-Sunstedt. I do the same idea by applying, there is some local rule, but more complicated. There are 7 or 8. So I do the same, and as soon as you know 3 of this, you know this. But now in each vertex, it's not an alternating word in white and black. I have to know from this to this is operator A. So this is supposed to be white, yes. So you have to know which See, A, you have to know which of the two you are going to replace this one by this. So it's word, but one of the white cells have a mark. That's the element in the diagram. And then, chop, 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 you apply a local rule coming from the commutation. And you get bijectively an alternative tableau. Inverse bijection. To convince you, if I have, oh, I am 58, I have 1 minute more for 60 minutes. Inverse bijection. So you know you can fill up all this, and the rule is that you start with a white cell, and then if you go down, you can look that you cannot use any operator S, because as soon as you use S, it's a black and there is no more white cell. So you are forced to do only K. Now, here, at the end, I want to have only one, the Laguerre history, you start with one white letters and you finish with another white letters. Maybe there is some black here. But now here, I am forced, I can use the operator A on the edges. But as soon as I use A, I'm creating 2 or 3 or more white letters, and I will never be able to go back to 1. So I am forced to put J. And then I am forced to do the local rule. Chop, chop, and you do this in every order, chop, 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 and you get the permutation. This is a reverse bijection. So, 2 bijection for 1 theorem. So what we have done, we take an alternative tableau at the beginning by the exchange fusion inverse algorithm, we get sigma. Now by knowing all the story of Laguerre, history, Fomin, Young tableau, Heuritzke, I'll get another local algorithm. Question, what is the relation between these 2 bijections? Sigma equal tau minus 1. And that's the way I found this bijection. I first found tau. It was very difficult to put it in a nice way. So, but I was looking that some value x, I, and I plus 1 was exchanging in the local rule. And you know, in the Breuer order, it's better to exchange consecutive I values index. So I say, okay, let's inverse everything, and let's do it this rewriting rule in terms of the inverse permutation. And the proof is that what emerged from this is a kind of jeu de taquin. I have no time to show you, but there is a kind of jeu de taquin on the grid, and if you transform this jeu de taquin, it's easy to show that it's exactly the bijection of the beginning. So I will finish, if you allow me, some perspective. So now, so you know there is some solution of the general Askew-Wilson, the general problem. There is a very nice paper using Askew-Wilson polynomial. There is some paper using Q-Hermite, so orthogonal polynomial is behind the scenery. There was Laguerre history. In fact, this is a Askew-Wilson classification of orthogonal polynomial by the lower level that Hermite, then Laguerre, Charlier, Jacobi, etc. And you see this is the moment of the orthogonal. The moment of Laguerre is n factorial. What we have, Laguerre history, was related to this tableau. Here you have Chebyshev, which are Catalan, or the biggest of the binary coefficient. Hermite is involution with Charlier. And you have seen, if you were there at the first meeting 2 weeks ago, there was, in the talk of Prelberg, some bijection with involution. This is involution with no fixed point. And some paths, dig paths with some label. So this is Hermite history, which is a particular case of Laguerre history. And many people also, in Cracovie or in Duchamp and Blasiak, and there are many people working in. It's well known that when you do the creation and annihilation operator, there is a Stirling number appearing. So if you make a creation, deletion, and you repeat it 10 times, then it's related to the Bell number, so it's a Charlier history. There is also a Charlier history. And then combinatorics we have done until here. Maybe there is interpretation, but this is the top of the mountain to reach, and we don't know how to do the combinatorial with Askew-Wilson. Now with all this, I believe that the Laguerre history, you can't go until the top because of the PASEP. Some other perspective, there is a recent paper during in archive last or 2 weeks ago about there is this is for you, Alain. All Littlewood function in non-cotative variable. There is Tevlin basis, and there is some change of variable or basis from one to another. And the conjecture is that the coefficient which is involved is exactly the number of permutation with a given Genoki shape and the inverse with a given up-down sequence. Which means here you see you have to count how many such alternating tableaux, but you give more, you give also the up-down sequence of the permutation. You give the up-down sequence and the indices of the advance, and this there is some very interesting conjecture about this. So in conclusion, we have seen alternating tableau, we have seen a lot of alternating word, alternating Genoki shape, and a tableau in alternating is sign matrices. And this is in fact the first part of the talk. The second part of the talk is this, which rendezvous in Vienna. I will give the second part in May. But you know, this is to practice. I am Bordeaux close to the Pyrenees, so I practice very much. This alternative tableau is just a new route to climb Mont Blanc, which is very classical. And in Wien, I will put my base camp to go to Himalaya, to climb the Virgin Mountain, Razumov, Stroganov. I don't know if we will do anything, but at least I will propose a route analog. And as this is a video, supposed to be a video preprint, I have to thank Professor Razumov and Stroganov because we get a grant. This means matrice, assigne alternant, and Razumov-Stroganov conjecture. So we propose a project to solve the conjecture, but it's only 3 years. In fact, we need 30 years. Because we want to stay in the forest. We want to solve it in a combinatorial way. For us, we stay in the jungle. The forest is very difficult. You physicists, you go in the plane. You go above the forest. But for us, we have to do all of this elementary step, and it's 30 years. And even if physicists solve it, we are very quiet because, okay, we will give a bijective proof. Or maybe a half bijective and maybe more and more. So it's take look the Schaeffer bijection with planar maps. It was taught 60, and then Corey Vauquelin 80, and then some other people, and then Schaeffer came. So in 40 years he came. So maybe Razumov-Stroganov it will be 300 years and no for combinatorist. Okay, so here it's some paper website. So everything will be on the web, and I will put more reference because it's really a preprint. So okay.
Any questions about any of this?
Yes?
I have a remark and a question. Remark, thanks for the beautiful talk. I felt aesthetical and mathematical pleasure. But I also can tell you that you might increase the speed if for these relations you apply algebraic methods like diagonal limit, because these normal forms are straightforward. This is a Grobner basis, and then you get this words.
You are talking of the speed. Which speed? The speed of the particle, the speed of the talk, or the speed of the proof?
The proofs. Maybe some proofs can be.
But,
I don't claim, but my guess is that some proofs. This is very beautiful to use this.
Thank you very much for the compliment.
Yes.
But the proof, you see, such paper, probably there is, to write the paper is impossible. So this is a video paper. It's a, but now it's a,
No,
yes, the Grobner, yes, you explained me the Grobner base. Yes, yes, I will look, yes.
These relations, I guess,
Yes.
it's obvious. If you order correctly the variables, they are form a Grobner basis, and then what you wrote as normal forms, it's straightforward. You don't need the proof. You just apply it.
And you, because you're, this is a very trivial particular case of your beautiful theory. So do you think I need to go through the deep thing you are doing just to do this to improve? Yes, yes. No, I take it. No, but no, I confess that this is, as an algebra, it's easy, it's trivial, but Grobner basis or what you explained to me is much more rich subject.
Yeah, that's
So it's just an example. It's a particular case. Yes.
Any other comments, compliments, questions? Criticism? Okay, so let's thank Xavier.
Thank you.